All right. So this lecture, basically, which was covered kind of in the last class, discusses the concept of capacitance in a MOSFET. You might be wondering, why do we have a separate lecture on capacitance? Because in a MOSFET device, there are a few characteristics that we care about. One is current voltage characteristics. The other one is capacitance voltage characteristics. Why capacitance, you might ask? Capacitive properties determine the speed of a device. Okay? So there you go. Do you care about the speed of a device or not? You probably should. And also current voltage characteristics, not just, current voltage characteristics deals with the speed as well, but it also deals with the actual functionality, whether that device even turns on or not, or turns off or not. So depending on the current level, you can judge whether a device is on or off. And based on the capacitive property, you could basically understand how fast or slow the device will be. Okay. And there are many other advantages of, in fact, in chip design, in VLSI industry, we don't really use discrete capacitors. We use MOSFETs, quite literally MOSFETs as capacitors. Okay, I'm going to fast forward. I will assume that if you review the recorded lecture, I tested the recording and I think it should be okay. Basically touches upon all the important aspects. If you review the lecture, I hope you will be at a stage where you understand this figure. I want to start from this diagram. In fact, yeah, this diagram, which is the most important concept in this particular lecture. The CV property, the capacitance voltage property of a MOSFET, which, by the way, we experimentally measure. So if you have a MOSFET device, or if you design a new MOSFET structure, you do two kind of characterization at the minimum. You test current voltage property, which will be the topic of next lecture, and you test capacitance voltage property, which is the topic of this particular lecture. Okay, just two characterization will suffice. When industry does it, they make thousands of device samples, and they have automated testing setup that gives you, humongous number of CV properties, IV properties. So they measure IV 1,000 times in 1,000 different devices to make sure they capture the reproducibility of the properties. It's not just a, accident. Like you get the same or similar IV across multiple devices that you make and multiple cycles for the same device. So it's reproducible. Making sense? So the way they test the device property or how good or bad the device is based on two properties, current voltage and capacitance voltage. So you're looking at one of them. And this particular graph is the most important thing that you should care about. See, it covers a lot. Just by looking at the CV property, you could understand where the threshold voltage of the MOSFET is. Isn't that interesting? Remember all those discussions we had in the previous lecture about how to calculate threshold voltage? This is the equation, metal semiconductor work function difference, all those good stuff. Well, nobody does math in actual real life. They do experiments. Now, they used to do math. You do the math when you're just developing the device. But after you're done developing it, it is a matured device. You're just optimizing it. You basically do experiments and figure out the threshold voltage like this. Measure CV, and the minimum point will tell you where the threshold voltage is. Interesting, is it not? So wouldn't you do this type of characterization in the lab? This is one of the reasons why I do CV characterization. Number two, remember flat band voltage? So there is a way to figure out flat band voltage from these characteristics, and this equation shows you. We can calculate the flat band capacitance, and depending on where that capacitance arises, you can calculate the flat band voltage as well. So this CV characterization allows you to extract different information about the MOSFET itself without having to go through material level parameters. You could just do it macroscopically, just measuring stuff. Still with us? With me? Okay. All right. Now, 4 different modes of operation for MOSFET. We covered them at the very beginning. I don't know if you remember this. Accumulation, depletion, practically inversion, but you could divide it up into 2 parts, moderate inversion and strong inversion. Okay. Because why do we divide up inversion into 2 parts, moderate and strong? Because of CV property. And I'll talk about it very quickly because I think it was covered. So in accumulation, you have an almost constant capacitance, oxide capacitance, COX, which is practically governed by the oxide, metal oxide semiconductor. Remember, that's the MOS of the MOSFET. There is an oxide there. and the oxide determines the capacitance level. So there is less interesting stuff, but more usable stuff. You sometimes want to have a constant capacitance, and you get it in the accumulation region. So if you are trying to use a MOSFET as just a capacitor, you might want to use it in the accumulation region, or you might want to use it in the inversion region. Are you still with me? So in both cases, you have constant capacitance. But meanwhile, in between this, during depletion region and moderate inversion, you have non-linear capacitance. So that's where things change a lot, dramatically change a lot. So if you're trying to design a capacitor with a MOSFET, you wouldn't like to operate in depletion or moderate inversion. You want to make sure it's strongly inverted or it's in the accumulation mode, so that you can use it as a constant capacitor. I guess all good? And the reason behind having this non-linearity is this diagram. Or maybe let me go back all the way to here. See, I'm almost reviewing this the lecture. Okay, please pay attention. I'm gonna be very quick, but I hope it will add something to the previous lecture. Okay, number one, accumulation. When you apply a voltage, like for example, negative voltage to the gate to invite the holes in the p-type semiconductor, basically you have positive charge accumulated here and negative charge present in the metal layer. And that's what you see in this diagram, don't you think? The reason why this column is in the upper level and the other one is in the opposite direction is because you want to show that this charge is positive, because there are holes piling up here, and the other one is the negative voltage that you applied and that has created negative charge. That's why you have two different directions. Make sense? And it's very simple. You apply negative charge, positive charges come in, and their majority, there is no other concept of depletion and whatnot. They're just coming and piling up closer to the surface. So essentially, it's like, separating out negative charge and positive charge at a distance. Practically, parallel plate capacitance. Parallel plate capacitance is a constant capacitor. So there you go. Who's determining the distance? The oxide thickness is determining the thickness, right, of the parallel plate capacitance. So essentially, if you calculate the parallel plate capacitance of this oxide, you get the level that you have here in the depletion mode, oxide capacitance. Are you guys all good so far? Okay, go back to this one again, one more time. What happens in the depletion mode? When you apply positive voltage to the gate, holes that are also positive charges are repelled away from close to the surface, and electrons that are minority charge, they gradually pile up here and create some form of capacitive coupling. Okay? But importantly, you have a depletion layer of charge. So you deplete this layer from holes. So you have a depletion layer, and on top of it, you can create some additional electron that can pile up here. The stronger the inversion is, the more electrons will appear here. So apparently you have two aspects here. One is the electrons piling up and positive charge at the gate. So you have a parallel plate capacitance option. Still paying attention, or am I making sense? All right. So when you apply positive charge to the gate, or positive voltage to the gate, you deplete the semiconductor surface. At the same time, depending on how much inversion you get, you can create some excess electron. They're minority carriers, but they will pile up closer to the surface gradually. They will be slower. They're not as fast as the holes, because holes are majority carriers in p-type semiconductor. They're everywhere. They can easily pile up. But it will take some time for enough electrons to pile up closer to the surface. So just take a look at these two diagrams. This is a parallel plate capacitor. This is also a parallel plate capacitor. The only difference is here, negative, positive, here, positive, negative. But do you care? You don't. Essentially, it's a capacitor. You just have to separate out positive and negative charges at a distance. You get a capacitor. So essentially, they are both the same. They're both Cox. oxide capacitance. Okay. When you go to strong inversion, the only thing that responds to change in gate voltage is this layer. This layer just keeps, let me show you here. This layer, inversion layer, just keeps getting bigger as you increase the voltage. So the only layer that responds to voltage is this. So the only capacitor that matters is oxide capacitor. But when you are not really that inverted, you are close to inversion, but you're not really that inverted, then there is an interaction between this oxide capacitance and the depletion capacitance, because you can have more and more depletion, for example. Okay, so when you have two capacitors in series, you have to think about the equivalent capacitance. And since the depletion capacitance gradually changes, the equivalent value changes. That's why you have this non-linearity in the middle. During the depletion mode and moderate inversion, you have non-ideality, because there is an interplay between the inversion layer and the depletion layer. Okay, but when you are strongly inverted, the only thing that matters is, you know, this. Let me show you again. This layer, inversion layer. That's why you are back to COX again, and here you are back to COX. Okay, and I noticed that Mazhar covered this slide, which shows basically whatever discussion you do with p-type substrate, it's kind of like a mirror image. You can just take a invert for the n-type substrate, because wherever you get accumulation, you get strong inversion for the other type. Like basically the voltages will be inverted, right? So essentially we could all, but basically whatever discussion we have had on NMOS, or we could also do for PMOS, just inverting. I noticed that this slide was also covered, which talked about the high frequency characteristics. Can anybody explain to me, what happened at high frequency with the CV? Let me just draw in red. The red line shows you the actual CV that we expect to see at lower frequency when you measure slowly. What do I mean by lower frequency? You ramp the voltage slowly. You take a microsecond to ramp, or a millisecond to ramp from 0 to a voltage VDD. But when I say high frequency, maybe you take a nanosecond to ramp from 0 to VDD, like you are doing it very fast. What's wrong there? Notice only so in the accumulation mode, nothing changes. Only the inversion mode gives up. It doesn't reach the oxide level. It basically, gets saturated at a lower level. Why is that? Can anybody tell me? It was all mentioned here, by the way. Cannot change instantly, blah, blah, blah. All of these are mentioned here. I'm just trying to see if you guys remember or paid attention. Can anybody explain? What's wrong here in the inversion mode? Why not the accumulation mode changing? No one can answer as all right. So it wasn't clear to you, looks like. Makes sense to repeat the discussion and tell you what that is. I just gave you a hint in the last explanation. In the depletion mode, you are dealing with holes that are majority or minority. Quickly. For this semiconductor, are they majority or minority? Holes? Majority. There are more of holes, like they're everywhere. Is it easier for us to pile up enough holes closer to the surface to create the capacitor or not? They're everywhere. I need 10 holes. Come on, we are there. But inversion takes place through minority carrier pileup, which is like electrons. There are few electrons in the p-type material anyways. So you have to collect enough of them to pile up and shadow the charge that you are providing here. Don't you think? Isn't that a slower process? Okay, so there you go. So that's the reason why inversion can eventually achieve the same level if you give it enough time to collect enough electrons. But since electrons are minority carriers, it takes us time to generate and accumulate enough electrons to create the oxide capacitance. Okay, so if you do it really fast, electrons will just give up. Man, I mean, I cannot keep up with that. Just do your thing. So that's why this capacitance saturates. right here. Still with me? So depending on how you measure, you could either get this type of CV, or if you give it enough time, you could get this type of CV. Okay. Now, based on this understanding, tell me, if you're trying to just make a capacitor out of a MOSFET, just make a capacitor. You don't want to use a discrete capacitor like you must have used in your PCBs and stuff, right? Then which mode do you prefer? Accumulation and inversion. From the previous diagram, it looked they were the same. But based on this understanding, you should probably care about, tell me, left or right? Left or right? Left, which is accumulation. Okay, because this is stable, irrespective of whether it's high frequency, low frequency, blah, 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 right? Okay. But for all practical purposes, think of this. When you're using a MOSFET, you're not really using it in accumulation. You are always using it in inversion. We always care with, basically deal with inversion. And that's our next lecture eventually. So we have to be mindful of this frequency dependence of capacitance, CV. Okay, that's the only take-home message from this slide. And the next slide, which shows you another very simple concept. I know it looks very busy and scary, but if you give me like 2 minutes of your attention, we'll be done with this slide. Ready to do that? Okay. This is the CV that we just finished discussing. Tell me, is it high frequency CV or low frequency CV? High frequency, because this guy couldn't go back up and create COX because I didn't give it enough time. So this is the signature of high frequency CV. For the most part, do you care about low frequency stuff or high frequency stuff? You know, in modern world, we always want things to be fast, so high frequency. So moving forward, most of the CVs that you'll see will have this type of a shape. Okay, we're not going to show something like that. All right. Anyways, now notice that all these other lines show what happens when you have a fixed oxide charge. So MOSFET is, you have a metal, you have an oxide, and you have a semiconductor. All interesting action will occur at the semiconductor layer. But oxide could also have some impact. Oxide can have fixed charges. And I told you that before, we didn't really discuss this to that degree. It could have fixed charges, basically stuck. What do I mean by fixed charges? They don't change based on the voltage. Doesn't matter what type of voltage you apply, these charges will always be the same. What is the source of that charge? Remember, just notice this interface. At this interface, oxide, which is a silicon dioxide, and semiconductor, which is silicon, they are two different materials. Their lattice will not match perfectly, don't you think? They will have different lattice structures. So at the interface, there will be broken bonds. Don't you think? Just try to fit two different kinds of tiles at your on the floor. The layer where they match, there will always be mismatch, don't you think? They will look different. You could easily figure out that there is some asymmetry there. So when silicon oxide and silicon meet each other at the interface, there will be broken bonds. And that broken bonds typically lead to positive charges. Typically positive charges, okay? It's very exceptional to get any kind of negative fixed charges in oxide. Okay, now, based on that, do we have any control over the interface? Can we control how many fixed charges? No, we cannot. But we can measure experimentally how much fixed charge we are getting in the oxide layer. And the way to do so is to use CV measurement. That's the other reason why you do CV measurement. Okay, so hopefully every slide will show you why we do it and how can this be used. So turns out the more positive charge you get, this CV shifts to the left. So this is what this thing indicates. Notice this QSS is the trapped surface charge. Greater than 0 means it's positive. So this is typically positive. And as you see, the more positive it gets, the more left shift you eventually achieve. Okay, and that changes the flat band voltage as well, by the way. This is the flat band voltage. The flat band voltage shifts with the trap charge. If you have more positive trap charges, the flat band voltage will shift as well. But at the very least, Just by looking at the shift, there are ways that we could use to back calculate and tell you how much trap charge you have in the oxide. So you basically can calculate QSS. Otherwise, just imagine for a second, just, you're trying to make a business out of semiconductors. Each and every one of them were a major roadblock at some point. And we may not really pay that much attention about it, but this took away somebody's sleep for several days. Some engineers sleep, if you think about it. Okay, we make MOSFETs, but they don't turn on at the voltage that I wanted it to. Why? Because the flat band voltage shifted. Why did the flat band voltage shift? Because there are fixed charges in the oxide. How do I know how much fixed charge I have? That's the question. So what do? So people do a lot of characterization, and somebody noticed that, oh, based on how much trap charge you get, you have a fixed amount of shift in the CV. And we could back calculate and tell you how much fixed charge is there. And based on that, you could calculate the flat band voltage. Am I making any sense at all? Okay. So if you're an engineer, you go to the lab, you measure CV, you know the CV should look like this, but it looks like this instead. So based on the difference, you could use some maths and some equations and calculate how much fixed charge is there, and you could put it in and calculate flat band voltage. Done. Now you have more accuracy, more predictability. Making sense? And by the way, one more story. You are Intel. You are trying to make a new MOSFET. You make a sample and it looks like this. You go through some optimization. How do you know the second, trial is better? How do you know the second trial is better? Let me show you. Let me ask you two questions. Green one, option A. Oh, not blue. Which one can I? Maybe yellowish. Yellow one, option B. So your second trial gives you either A or B. Which one will show improvement in process technology, that you have managed to do a better process that makes better MOSFETs? A or B? Which one do you like? A. Why? It's close. Yes, it's close with the ideal, meaning you have less trap charges. I mean, are you making a MOSFET to have random trap charges everywhere? No, you have more trap. If you have more trap charges, that represents your process is not that good. You have broken bonds everywhere. Okay, it might be okay for now, but remember, these trap charges lead to reliability degradation. Over repeated usage, they can eventually break down the oxide. Okay, and when I say breakdown, can anybody? Okay, let's not waste too much time. I can give you the example. The lightning, basically, thunderbolt that you see like Thor in the movie. Right? So the thunder is nothing but an example of oxide breakdown or insulator breakdown per se. So you have air, which is an insulator. We don't always get the thunderbolt because you have an insulator. You have a huge charge piling up at the clouds, and you have ground literally at ground. But if the voltage exceeds a certain level, the insulator can break down. So you see, you have a direct connection from clouds to the ground, which you don't like. Similarly, the gate oxide is there to stop you from letting current flow from gate to the semiconductor. You see that? There is an oxide there so that current cannot flow from the gate all the way to the channel. But if the oxide breaks down, the device will be destroyed, as you can see. So if you have this type of fixed charges, like too much of these fixed charges, too much of these broken bonds, they can eventually lead to reliability degradation. So that's the other reason why you want to reduce them. Okay. So how can you justify as an engineer? You go to your boss and show him or her that I made the process better over the last weeks of work. See, CV B to CVA. Good job. You have done a good job. So you have to move it even to the right. So see, all of these things have more meaning in the actual industry than you have in the textbook. I could ask you a question to draw CV. Okay, blah, blah, blah. Like a random curve. Who cares? But they have used it in real life. Okay, moving forward to the next line. What if you have a different kind of trap? So one thing is fixed charge that don't respond to the applied voltage. They don't care how much voltage you apply. They will always give you one constant charge. But there are some other kind of charges. They're known as traps. Okay, they are voltage dependent. If you provide certain voltage, they get filled up. If you provide a different kind of voltage, they get empty. So these are voltage dependent charges. They are often called, interface states or interface charge, not fixed charge. The term fixed represents it's typically fixed, but interface charges could be voltage dependent as well. Am I making sense? Okay, so they are even more trickier to deal with, by the way. What is the signature of this kind of charge? And I'm going to show you. This blue line is not blue anymore. I'm just drawing on top of it. This is the ideal CV. If you have interface states, this CV will have a smearing effect, like, flattening out, something like that. So if you have more flattening, you have more interface charges. So that is a signature of having interface state charge. So you could, after you make it, I already told you in the very first lecture, MOSFETs are smaller than virus and bacteria. You cannot practically, and you make billions of them. And after you make them, how can you go down and see the interface? You'll be surprised to know the interface is like few atoms thick, 5-10 atoms. You cannot simply just go and see, oh, we have a bad interface. No, it's impossible. You have to use this type of macroscopic properties to back calculate and understand what's going on. So we do CV measurement again. And if you see this type of smearing effect in the CV, this is like a diagnosis system, by the way, right? How do you diagnose that somebody has high blood sugar? You test for some symptom, like how do you know that this guy has this problem? You do blood test or whatnot, right? You test for some precursors. Similarly, this is basically like diagnosing the MOSFET. If you see this kind of a CV effect, smearing, that represents that you have interface trap charges, which are more serious problems than fixed charges, by the way, because fixed charges are fixed and predictable. You don't like them, but you can live with them. But interface charges are tricky because depending on how much voltage you apply, they will behave differently, which is even more problematic. Okay? So again, now, if I ask you a question in exam, what kind of questions can you expect? Imagine you have a CV. I show you that you measure, this is an ideal CV that you expect, but you get this type of a CV. Is this fixed charge or interface traps? Fixed, because this is basically a shift. If you get a shift, that's fixed charge. But if you get a smearing effect like this, so keeping the center fixed, there are reasons why that doesn't change. I'm not getting into that degree of detail because I don't want to bore you and like scare you away from the field entirely. And trust me, I mean, there is no way to sugarcoat it. It's not an easy thing to do. Okay, if you want to get deeper, things get more complicated. But that's what some people like. Not everybody needs to like it. And if you don't like getting that deeper, fine. You can stay at the higher level, work with circuits and systems, and not deal with this deeper level issues, which is fine. You can still be on the chip design industry. Anyways, so are you good with that? So depending on the type of changes you see from the ideal CV, you could diagnose the problem with the MOSFET. So that ends this part. And this is the last slide of this lecture. See, this was an easy enough lecture, but I hope you see the significance of CV measurement. Okay, now this is the connecting slide to the next lecture. So I'm not going to do this here. I'm going to do it in the next lecture, right? So let's just set it. So basically, this sets the stage for MOSFET. So far, all that we're doing is we're dealing with MOS, metal oxide semiconductor. Let me draw that one last time. Metal oxide, and then you have semiconductor. We never talked about field effect transistors. We never talked about what does field effect mean, right? That's coming up here. So we will introduce two additional terminals here, source and drain, and show you how that could be integrated into like a device operation. Okay, and there are two kinds of MOSFETs based on our understanding so far. Remember, so far we have been talking about metal oxide semiconductor. Semiconductor could be P-type or N-type, right? So based on that, if this semiconductor is P-type, you bring in N-type source and drain. If the semiconductor here is N-type, you bring in the opposite kind as source and drain. So that gives you two flavors of devices, NMOS and PMOS, which we will discuss right now. So let's get started with the next lecture. Okay, so this is the lecture that will take us closer to the circuits. And we will end with some circuits, by the way, here. Very simple circuits. And the lecture after this will be fully circuits, digital circuits. Still with me? All right. The fact that we are moving from devices to circuits tell you something, that we are nearing the end of this course, 335, and moving towards 336, which will be electronic circuits, these electronic devices. Okay. All right. So metal oxide semiconductor, field effect transistor. I will start with a very simple graphic. And I request you to pay attention to this 2 minutes or 3 minutes of discussion. That will significantly make your life easier rather than going through the pages of description. So let's start. You have a semiconductor. Let's talk about P-type. P-type. And then you have metal and you have oxide, which is an insulator. Now, say if you have N-type, two other N-type regions here, N-type. If you have two other N-type regions here, what can you do with it? Let's see. So typically, at this interface, notice, this is essentially a PN junction. Don't you think? It's a PN junction. And this is again another PN junction. So you have two back-to-back PN junction. If you see from left to right, this cross section, you have two back-to-back PN junction. I mean, I could just draw it here this way, if you think about it, right? Two back-to-back PN junctions. Oh, sorry. Yeah. So I just wanted to clear this up. Now, on the quick question, if you have two back-to-back PN junctions, can you let any current flow through them? No matter which type of biasing you use, it will be forward bias for one diode, reverse bias for the other, or vice versa. Whatever you try to do, one or the other will restrict current flow. So you don't have any current flow. Simple. So not even when you apply a voltage, say you apply positive voltage here and negative voltage here, nothing happens. Like between these two terminals, this is source, this is drain. These two terminals are source and drain. Nothing happens between them because there are two back-to-back diodes. Okay. Now, if you apply a positive voltage to the gate, which we have been doing with inversion and whatnot. So if you apply positive voltage, the holes in the P-type layer, which are here, they will run away from the surface deeper into the body. The body is typically much deeper to allow that migration. So now you end up getting what? Remember inversion? So after they're gone, which color should I use? Let me use blue. So electrons, which were minority, there are a few electrons here and there, right? They will come and pile up closer to the interface. There's a very thin interface of electrons, which is the inversion layer. Isn't that what we discussed in the MOS concept, metal oxide semiconductor? We didn't talk about source and drain. We didn't need them. We just discussed this action so far, inversion. So inversion occurred. But all on a sudden, this inversion leads to something interesting. Notice, you have N-type here, which is like full of electrons. You have N-type here, which is again full of electrons. And you have a channel, which is also N-type. So essentially, this is all the same thing, as if they are all connected. There is not back-to-back diode anymore. You see, closer to the interface, there is no back-to-back diode anymore. So you somehow do the hard work to create an inversion layer, and all of a sudden, you have a short circuit kind of situation, like between source and drain. Now, okay, what will happen now? Nothing. The electrons will just stay where they are. Why will they move around? They will only move around if you apply a positive voltage here or negative, like create a voltage difference. If you apply positive voltage here, electrons will feel like, hey, I like positive voltage, so let me go out from here to the other side. And the source electrons will also feel, hey, I like that positive voltage as well, and I can go through the channel to the other side. So let's go. See the point here? So from source, you'll have a constant flow of electrons moving towards drain, getting out of the drain. So you create that by applying a positive voltage. Now, the moment you remove that positive voltage, what happens? This inversion layer is gone, and you have back-to-back diode again and no flow. So being on, where current is flowing, to off, no current flowing. Very simple concept, don't you think? You could do the exact opposite, like basically the same thing, with exact opposite combination. You could start with N-type body and P-type source and drain, and gate and oxide could be the same. And now you see, if you apply negative voltage to the gate, like basically the opposite situation. Does that make sense to all of you? So this is the concept behind the N-type MOSFET and P-type MOSFET. Oh, so sorry, both of these are N-type. This is P-type MOSFET. Are you guys all with me? Why do we call this NMOS despite the body being P? Because look at the channel. The channel is the celebrity here. Channel makes or breaks a device, okay? When you create a channel, what will be the channel type? Will it be N-type or P-type, folks? Think of it. N, right? Because these are N, so you have to create N. On the other hand, here, you have P-type channel. So that's why it's called P-channel MOSFET, or in brief, P MOSFET, or just PMOS. And this other one is NMOS. All good? Super simple concept. And I told you that this concept was dreamt or thought of by someone in 1925. Did I tell you that story, right? Wrote down something on a piece of napkin at a restaurant, and eventually that was patented. Nobody could make it for 50 years. And like, okay, we went through a lot of migration, like vacuum channel to diodes to BJT to eventually finally MOSFET. But by then, like, 1925, too long ago. But eventually that dream was realized. So we started with that dream. We wanted to incorporate this feature in a device, but technology wasn't ready. So the fact that we discussed just MOS in the previous lectures doesn't mean that's where things started. Things started here. That was the original vision. But just to help explain the idea easily, we got rid of these other two and just focused on the MOS to help you understand the concept. And now let's bring into additional things to see how they interact. Okay? All right, now, simple concept. We are not going to keep drawing this complicated structure anymore. We will just use a symbol. So basically, let me just fast forward here. This is the symbol that we'll be mostly using. There are different symbols in different textbooks. So I wanted to show you this. These are symbols for NMOS. These are symbols for PMOS. I mean, we like simplicity, so we will be using this and this symbol for NMOS and PMOS. These are all symbols. We don't care. Okay? But you might see different symbols in different textbooks. Okay, let's go back here again. Few other, to preempt some questions, which I'm not getting, for example, why is it N plus? Notice, source and drain are always degenerately doped. N plus and P, right? N plus and P plus. Keep that in mind. You know that N-type material and N plus material, they have the same property, except for the fact that N plus is more seriously N-type. Like they have more electrons, right? So apparently, why do we call this source and why do we call this drain? The name should give you some hint. We use this terminal as source of electrons. When you apply positive voltage to the gate, this terminal provides the electron that drains out of the other terminal. Now, does that make sense, folks? So if you have an N plus layer that gives you less resistance, and it's almost like metal, they don't have any other purpose but to serve and catch electrons. Give me electrons, take electrons. That's it. So you need to make them as good of a conductor as possible. Okay, that's why we have N plus or P plus material in that layer. Are you guys all good? Okay. I mean, I'm expecting question at every step of the way, and please feel free to ask me question. You are letting me go so easily. First, second, why is it this guy is not P plus? Tell me. This is just P, not P plus. There are multiple reasons. I'm going to give you one that will be easy for you to understand based on the concept of 335. But there are other reasons. Keep that in mind. Okay. Number one, how many of you remember this equation? Np equals Ni squared. And I told you that the number of electrons and number of holes in any semiconductor the product of it will always be Ni squared. So if you create a lot of holes, like by making it P plus, if you make a lot of holes, what will happen to the number of electrons? Tell me. Much less, right? If one of them goes up, the other one has to go down to keep the product the same, right? So if you make this P plus, electrons are already minority. You are relying on these minority electrons to create the channel, which is the most important thing, right? If you make it P plus, there will be even fewer electrons. So it will be even more difficult for you to create an inversion layer, which you really want. So let it be P rather than, does that make sense? Okay. Other quick question could be, why don't we just make it N type and just keep it in, make it easy for them all the time? Then how do you turn off it's not a switch, it's always on, right? What is the use of something that is always on? You could have just used a metal instead, just connect them, right? So that's why there are reasons behind all of this. Okay, let's move on. Notice between these two diagrams, there is a difference. What I explained so far, this is the concept of enhancement mode MOSFET. And what does that mean? So in this type of MOSFETs, you don't have the channel. You have to create the channel by applying appropriate voltage. So you have to, at some point, people used to use this term. You have to enhance the channel to turn on the device. So that's why it's an enhancement mode MOSFET. And at the time, decades ago, by the way, people used to use a different kind of MOSFET as well, which always had a channel, like it's always there. You have to apply some voltage to disrupt the channel, to close the channel down. So the first type of device is generally off. You have to apply a voltage to turn it on. The depletion mode device was always on. You have to apply a voltage to turn it off. Exactly the opposite. Does that make sense to all of you? Okay. So they look complementary, don't they? Don't you think like one of them is always on, the other one is always off? People used to use this type of complementary devices to design complementary circuit. How many of you have heard the term CMOS? What does C mean? Complementary. A complementary MOSFET. Okay. CMOS literally means complementary MOS. And you see the complementary nature here. One of them is always on, the other one is always off. So, but this is not really the complementary that we use today. Because at the time, people didn't really know how to make the other kind of MOSFET because of process challenges. You know, we often underestimate how much effort it takes to make things work. I told you, 1925, the concept was there. The concept was there all along. People couldn't make it because it was impossible to make using the process technology. Similarly, for the longest time ever, we couldn't make PMOS. See that? We couldn't make PMOS. We could only make NMOS. Or the PMOS was really, really lousy, really bad. Okay? So, serving no purpose. That's why we used to rely on NMOS, both NMOS. But one was an enhancement type, the other one was depletion type. But now we can make really nice, beautiful PMOSs, as good as NMOSs. Okay, so then who cares about depletion mode? Nobody. So we no longer use depletion mode. You might be wondering, why did we decide to keep the enhancement mode and discard the depletion mode? Why not the other way around? Can anybody give me the reason? Folks, I'm taking the time and I want you to think about it. At some point in your life, all you have to do is think and solve problem, not write equation and solve maths and get grades. At some point, do you know my CGPA from undergrads? Anybody? I bet you, even if you try, you'll not be able to figure that out. It could be very good. I mean, but who cares? Nobody cares. When they gave me the job, they didn't even ask me for my undergraduate or even master's diploma. They all, oh, you're getting PhD from, okay, fine. The terminal degree. And they don't even know my PhD, the CGPA. It could be 4, it could be 3, it could be 1. It could be anything. So at some point, I mean, I'm getting ahead of myself. At some point in your life, the only thing that will matter or help you is your thought process and being able to solve problems. So this is more like a place for you to practice that, and don't hesitate to be wrong. Just give it a shot. They're your friends. At some point, you'll be in a room full of your competitors, not your friends. Okay, your colleagues will look like your friend. You can go and have coffee with them, but in the end, you'll all be judged. And maybe when it comes to laying off, 50% will be laid off, and you'll be competing your. Don't you know people get laid off all the time? Intel is currently laying off 15,000 engineers. Have you heard the news? Yeah, so Google did that. Microsoft did that. It's not just Intel. Like 1,000. When it happens in 10,000s. Just search. Google laying off thousands. Anyways, so it happens all the time. I mean, there is nothing wrong about it. They restructure, they re-strategize. Oh, we no longer care about AI. We'll go for blah, blah, blah. Okay, sure. Fire all the AI engineers and go some other place. That's not happening now. It's actually the other way around. But things change. Every time something changes, people get fired and people get hired as well. Anyways, so getting back to the point. Can anybody try to take a stab at it? Why do we care about enhancement mode? Where it's always off, you have to do some work to turn it on. Whereas you had a device which was always on, you just had to turn it off, right? Yes. Thanks for the answer. It's not really the right answer. Why? Because it's actually doesn't matter, because you could just flip 0 and 1 that way. Okay, doesn't matter. But that's a very good point. But that's not the right point. Yes. No, remember the point. You could turn it off, by the way, by applying a voltage. The other one is always off. What is the point of using something that is always off? You have to also turn it on, right? Does that make sense? So both of them are switches. Like, you see switches, like something that is always on, you could turn it off, or something that is always off, you can turn it on. Both of them are switches, but we prefer to use this one for our generation. There was a generation where the other one was also used, but in our generation, we only use the enhancement type. Please give it a shot. Yes. Thank you. And basically, there is one more step that we need to go, and I can help you guys cross that bridge, but this is the right direction. Energy. Let me tell you what. How many transistors do you think we have in our Core i7 processors? I told you the number. Is it in thousands? Billions. Most of these, almost 95% of them, are unused most of the time. Even more than 95% is unused most of the time. Imagine if all of those transistors are on always, and you only have to turn them off selectively. Wouldn't that be a tremendous waste of, when the transistors are on, current is flowing, so it's taking a power. So that will be a tremendous waste of energy. So that will drain the batteries like crazy. The fact that we're going for VLSI, like large scale integration, billions and trillions, we have to make a call that, hey, we'll need devices that will always be off. Only when I need them, I'll turn them on. So we chose enhancement mode. Got it? Okay, let's move to the next one. All right. So a repeat of what I discussed, but this is a realistic, real device. This is source. This is drain. This is gate, metal and oxide. Basically, this is metal, and this tiny little thin layer is the oxide. Okay, oxide is very thin actually, and then that's your channel. You see how thin that channel is? Like really, really, really small. This is already an electron microscopy image, right? Really small, and electrons flow from here through that channel to the other side of the drain and get out. And this is at least decades old. Modern day MOSFETs are way smaller. And like I said, you can count the number of atoms between source and drain. And that's in tens, not hundreds. Few tens of atom, 10 atom, 12 atom, something like that. So things are crazy, I'm telling you. Things are, I mean, this is beyond science fiction, I think. Anyways. Okay, so this is another easier representation of the structure. Still with me? Okay, just to show you that at some point we used to use polysilicon gate instead of metal gate. But don't worry about it now. For our sake, it's always going to be metal. For your generation, it's going to be metal. Okay, so moving forward, we covered this already. I also talked about what is enhancement mode, what is depletion mode, and we only use enhancement mode devices right now for digital electronics. I just told you that. And this is another 3D version of the MOSFET structure so that you have a better look. Okay, let me show you one more time. This is source, this is drain, this is gate, and this is oxide. Underneath, this is oxide, really thin layer. You might be wondering, what are this? Can anybody guess? Can anybody guess? How can you apply a voltage to a MOSFET? Can you just connect the wire to the semiconductor directly? No. Why not? My question is, why not? Why can't you just take a wire and connect it to an N-type semiconductor? There you go. Do something, right? It's not going to work. Why? We had a separate lecture, and I actually deliberately added that lecture to this course because I think this is important. Heterojunction. Remember, there are two kinds of connection between metal and semiconductor: ohmic contact and Schottky contact. Schottky contact, you don't like. Ohmic contact is good, right? So how do you know that when you connect something to a semiconductor directly, it will be ohmic? No guarantee. There are so many considerations. Remember, right? Even if you don't remember, it's okay. But you know that that's a concern. So you create that at the process level. You create metal. This is metal. This is basically metal. So you create a connection between metal and semiconductor. Metal and semiconductor, and you ensure this is ohmic contact or almost close to ohmic contact. And now externally, when you apply a voltage, you just connect the wire here to the metal. You don't care. You're connecting metal to metal. No Schottky, no ohmic. Like, it's always good. You're not connecting metal to semiconductor anymore. Are you all good? Okay. So that's the reason why these structures are important. And trust me, if you search in like any job portal like Intel, TSMC, whoever, there will be engineers who specifically work on packaging, like packaging engineers. So this is part of packaging, by the way. Like, how do you actually make it usable? Anyways, so moving forward to the next layer, we already covered the symbols. Now, this is interesting because we covered one type of band diagram so far, and I'm going to show you that. And I hope that will ring some bells. I told you that this is a MOSFET structure. There are two ways to look at it. You can go through this cross section vertically through the metal. What are you going through? You are going through the metal oxide semiconductor. So you have metal oxide semiconductor. When you draw a band diagram, didn't we draw this type of band diagram a lot? Right? Basically in the last lecture, lecture before that as well. So we talked about inversion and how electrons pile up and whatnot, those kind of stuff. Okay, but there is another direction from left to right, which we didn't see before because we didn't talk about source and drain. That's what we are going to do right now. Still with me? I'm going to ask a couple of questions. What does this situation represent? Is this XX or still YY? What is this diagram? YY. Metal, oxide, semiconductor. Sure. Why is it flat? Why is it not carved like this? What does this represent? Which condition does it represent? We use the term many times. Flat band. Remember flat band? Bands are flat. So basically we start our discussion with flat band condition, and then we decide what happens. Does it bend this way or does it bend the other way? Is it accumulation or is it inversion? If you don't remember, these are recorded. So now I can, this is good, because I mean, when I used to teach this last like couple of times, it was challenging because it felt like after a few lectures, nobody even remembers anything. So I couldn't just share anything with them. I had to repeat over and over again. So now we have, that's the reason why I got motivated to start recording and sharing it openly. So you could look at it or listen to it at your convenient time. And even if you forget, I bet most of the courses that you have taken so far, you hardly remember 10% of each of these courses. Am I right? Or unless you're prodigies, okay, you might be. I mean, some of you might be, I don't know, but most of us are general people. So it's impossible to remember everything. That's how human mind works. If we remember everything, we'll be mad. Like we'll be basically insane, right? We don't remember everything. Like if you're mad at someone, you'll forget a week later, but you'll not be as mad. You might remember, I was mad at you, but not as badly as you were at the moment, right? So forgetting is a good thing, by the way. In fact, that's what people are using for AI hardware design. Like, can we introduce forgetting, or like basically taking things in the background rather than always remembering everything? Is that hindering the development of human-like intelligences? Anyways, sorry, I'm taking tangent here. It's going back. So let's talk about the other cross section, x dash cross section. Let's do that. I'm going to draw it in a very simpler way. So you have N, P, N. I like to use this one. Let's do this. N, P, N. So we are going through this cross section. I'm going to draw the thermal equilibrium condition first. And I hope by now you should be confident enough to give it a shot on your own. Let's do that. What happens to the Fermi level in thermal equilibrium? Will we have multiple Fermi levels in different sections, or will we have one continuous Fermi level? One continuous Fermi level. No matter how many materials you have, who is connected to what, we don't care. You'll have one continuous Fermi level. This is our Fermi level. So that's where we start in thermal equilibrium. So, okay. Oh, man, sorry. What happened? Did I? Okay. I think I erased it, but I'm going to draw it again. So just notice this. I just wanted to avoid confusion. I wanted to show you this. So this is our cross section. You are going through N, P, and N. So I will draw the Fermi level first. And now the first thing that I need to draw is an N-type material. And I told you this is actually N plus, and the other one is also N plus, not N. Okay. So how can I draw an N plus material? I will have to draw the conduction band and show that Fermi level is above the conduction band. And valence band will be somewhere down there. Good. N-type. Simple. What happens to the P-type? So in the P-type, this is not P plus. This is just P. So, this is going to be my valence band, closer to the Fermi level. And the conduction band will be somewhere up there. P-type. Again, N-type to the other side. So, N plus. So conduction band will be below the Fermi level. Valence band will be farther down. Oh, it's not letting me draw. Okay, sure. Now what do? What did we do for diode? Basically just connect them really nicely. So let's do that. Connect the conduction bands and the valence bands. Like connect the valence bands and the connection. Obviously I did too much here. Anyways, does that make sense to you? Let's go back and see this slide. Don't you see exactly that? What you don't see here is the valence band, because in some cases, some textbooks, they don't draw the valence band. It's so farther down, who cares? Something like that, right? Oftentimes they don't draw it, but if you draw it, it looks like this. Does that make sense to you? Can you draw it from scratch with just simple logic? Okay. Now, imagine you are electrons. You are sitting at the source. These are electrons. And also in the drain, this is N plus. They are also electrons. They're sitting at the drain. Can there be any movement between source and drain electrons? Why not? Who hampers the flow? Who hinders the flow? There is a barrier. Notice that there is a barrier. Exactly like the built-in potential for diode, except that it could be higher, much higher. Okay? So electrons don't typically flow from source to drain because there is a barrier. Now, if I find a way to reduce the barrier, remember when you apply positive voltage, kicks out the holes and creates an inversion layer. The way we could represent that effect in band diagram would be by showing this. And again, this is not basically drawing the valence band. Remember, this is just conduction band, but there will always be a valence band, okay? Down there. If you draw the conduction band, you could just shadow the other. Why is that? Can anybody tell me why is it so easy to draw the valence band if you have the conduction band? I told you this before. Because band gap, yes, the band gap will always be the same, e.g. So basically just draw the same line one more time, keeping the same distance. That's all. That's why, many textbooks, they don't draw both. Okay, so now if I find a way to lower that barrier, let me show the barrier lowering here, maybe this way. So the other one will also lower. Why would the other one also go down? Again, for the band gap. Just by, you are not changing the material from silicon to something else. It's still silicon. So the band gap will be the same, except the band positions will change. The conduction band will go down, valence band will go down, and stuff like that. So if I keep lowering the barrier enough so that the electrons can go over the barrier, that's how the MOSFET turns on. Am I making sense? Okay. So let me go back to this slide again. Let me erase the stuff that I drew. So electrons sitting in, they cannot go anywhere. Next slide. When you apply a drain voltage, first of all, let's start with that, drain voltage. I told you this before as a way to remember. When you apply a positive voltage, as if the Fermi level goes down, as if you have added a weight. When you apply negative voltage, it's like a helium balloon, the Fermi level goes up, right? We use that argument many times. So similarly, if you apply a positive voltage here, the Fermi level on the other side will go down because it's no longer thermal equilibrium. So electrons sitting here and sitting here, which in which side electrons will be happier, the drain or the source? Happy electrons, where? Source or the drain? What makes electrons happy? Higher energy or lower energy? Lower energy, of course. Anything in the universe prefers lower energy, as I told you, right? So electrons on the drain side are happier. So the source electrons will be jealous. They want to go. Here, by the way, they were not jealous. Nobody was jealous of the other guy because they had the same energy level. So remember, without any drain voltage, even if you lower the barrier, doesn't matter. Nobody moves anywhere. But, okay. Now, with drain voltage, still no movement because nobody can move anywhere because there is a barrier. Previously, even if there was no barrier, no movement because no inspiration. Now there is inspiration, but there is a barrier. So what do? You reduce the barrier by doing what? By doing, remember the same argument, applying voltage, kicking out the holes and creating an inversion layer. This process could be summarized or simplified quite easily in terms of lowering barrier. You're basically lowering the barrier. Yes, by adding a voltage to the gate, you lower the barrier for the electrons to move from here to there. Okay, so if you go here to this slide, these are all same color, so it's difficult to understand. But think of this case. You have lowered the barrier enough. Notice this is increasing VGS. By applying higher VGS, you lower the barrier further. So, if the barrier is low enough, the electrons can go to the other side and you have a flow of electrons. This is another way to explain using band diagram. Which one do you think the engineers use in industry? Always band diagram based discussion, right? Rather than using the cartoon and drawing. So if you see band diagram and band diagram lowering, even you use advanced simulators, they only show you the band diagram, by the way. Now, imagine you are an engineer. You're not going to design the same structure. This is done and dusted. Everybody knows how it works. But if you're trying to sell the next product or make the next product, you're going to make something fancy. So you create a very complicated device structure. And what you extract from the simulator would be band structure. You extract band diagrams, by the way. And you look at the band diagrams and try to understand, oh, you apply voltage, this reduces, that reduces. So that's how they analyze devices now. So you need to, you're learning the basics. Okay. So does that make sense to all of you? This is the other way to look at the MOSFET characteristics. Now, there is another way to relate that understanding to IV measurement. We talked about CV measurement today, and I told you how this could be wonderful. This could show you the presence of fixed charges. This could show you the presence of interface states, both of which could be detrimental. This could help you understand whether you are making any progress in your process design. Similarly, IV characterization is another important characterization that we use to see how good or bad the devices are. Obviously, they give you more information than CV, the information that you need to decide on your circuit design, okay? So we will get there. But first, let's see how the IV looks like. And this is the first slide that connects MOSFET structure to the IV. Let's do that. Still with me? If you pay attention, this is promise. This is going to be easy. So this is oxide. This is metal. This layer is metal. And this is semiconductor. This is, again, like a cartoon. And we have basically ignored the source and drain here, but imagine they're here. So S represents source, D represents drain. It's not me, it's a textbook, by the way. So I'm just explaining what the textbook shows. So let me start from here. Notice this. You have applied a gate voltage, which is greater than the threshold voltage. You create an inversion layer. Are you still with me? Why greater than threshold voltage? We had that argument before. Before the threshold voltage, you don't have any inversion layer. Without an inversion layer, is there any bridge between source and drain? No. There are back-to-back diodes. So no current flow. So if I ask you, like, it could be a question, by the way. This was one question in one of the previous exams for other 335 that I, the same thing, but VGS less than VT. Just draw IV. What should be the situation? Zero. No current. There's no channel. Ideally, no current, right? Basically, no matter how much. Okay, what are we plotting on the x-axis? VDS. So you're applying voltage between drain and source. No matter how much voltage you apply, if there is no bridge, how can they go from source to drain? Zero current, okay? So before threshold, nothing happens. So they start above threshold. Okay. So above threshold, you create a channel, and the channel is uniform between source and drain. So it behaves like a resistor. The channel is like a metal, like a metallic layer. Metals also have resistance, as you know. So it's like a resistor. So the IV is linear. What is the IV of a current voltage characteristics of a resistor? Linear. Don't you think? Right? So really nice linear characteristics. And this is known as the linear mode of operation for MOSFET. Literally, linear mode. There is another name, triode. People often use that term as well. Anyways. Okay. Now, when you apply even higher VDS, so as you apply more and more VDS, something starts occurring here. One thing that I didn't mention in the previous slide, why all of a sudden VGS, not VG? Let me go back here. I want to show you something. Was it here or was it? Oh yeah, maybe this will do. This will do. Maybe a simplified version. This one. We still have 1 minute. Sorry, I'm just going to show you one thing and then we'll stop. We'll catch up on this slide, this IV slide in the next class. So you don't just apply a voltage to the gate. You have to apply the voltage with respect to ground, right? As you know from circuit theory. So this substrate or body is typically kept at ground for NMOS. And when you apply a voltage source to the gate, you connect that to the body. So that's ground. And similarly, the source is typically kept at ground. And the drain is typically kept at a voltage, which is again connected to ground. So the voltage that you apply is VDS, the voltage between drain and source, or VGS, voltage between gate and source. And source is typically connected to ground with the body. Okay, does that make sense? That's why we use VGS, VGS, VDS. So that's why, again, we'll catch up. We'll start from this slide in the next lecture. I don't want to rush through it. So let's meet in the next class and finish this up. Thank you.